Welcome. Today we're going to talk about percent error. Now I first referenced percent error when we were talking about the definition of accuracy. If you look back at page 9, under accuracy it says the accuracy of a value can be expressed in terms of the percent error. Alright, so today we're going to be working with that percent error. Well, first of all, we need to know what error is before we know what the percent error is. So error is your results minus your expected results. So example, I expected 260 people, but 325 came. So 325, so my results minus 260, my expected results, that equals 65. So my error is a positive 65. Percent error is when you show the error as a percent of the expected results. Notice how it's bold, that means it's important. So it's a percent of the expected results. So you're going to divide by the expected value and make it a percentage. So my error is 65 still, right? So 65 divided by my expected value. So 65 divided by 260 equals 0.25. So notice how that's positive, right? You turn 0.25 into a percentage, which is 25. So a positive 25%. So 25% more people, because it's positive, than expected showed up. Let's apply this to some of the numbers we already worked with. On page 10, when we were applying our knowledge of accuracy and precision to lab situations, we looked at this data table. It shows 3 trials by 4 different groups, each of which was trying to measure the mass of a paperclip, which had a known mass of 1.004 grams. Remember, it's very important to know what is the known mass. In order to decide if something is accurate, we need to decide if it's correct or close to the accepted value. So let's apply this percent error to the data we've already used. When we first looked at this data, we decided that group 1 and group 4 were definitely accurate. But by looking at their averages, we could tell they were very close to the 1.004 grams. So let's look at group 2. Let's see how inaccurate they were. In order to do that, we need to look at their percent error. Now, first of all, we need an average. So 3.863287 plus 3.754158 plus 3.186357. That comes to 10.8. Now to find an average, we add them all up, divided by my number of measurements, 1, 2, 3. So 10.8 divided by 3, and my average is 3.601. And that's enough decimal places for now. So let's look at our average compared to our expected results. That's how we find our error. So error is results minus my expected results. Which in this case is my results were 3.601 minus my expected 1.004. Now if I were to do this, this would give me error, but error is not exactly clear. If I say I have an error of, 2.6, you don't really know what that means. However, if I say I have an error of 25%, you kind of understand something is off by about 25%. So in order to find percent error, we take our error and we divide it by the expected results. So divided by 1.004. So for group 2, their percent error by averaging all their measurements is 2.004. 5, 8, 7. But this is actually in a decimal form. We're not actually at a percent yet. We have to multiply by 100. So my actual percent error is 258.7%. They were definitely way off of the goal. An error of 258%, if you tell someone that, they understand that they were extremely far away from the goal. And therefore, they were inaccurate. Let's look back at your page 11 in your packet. So you must use the percent error formula below when performing percent error calculations in your lab reports. The formula indicates whether your experimental value, so your result, when you're doing an experiment, your result is your experimental value. So you have to decide if your result is less than or greater than the expected value. If it is less than the true value or the expected value, then the percent error will be negative. If it is greater than the true value, then the percent error will be positive. So percent error, the experimental value minus the true value, divided by the true value, times 100. Anytime we're doing a percent, we always need to be multiplying that decimal by 100. Remember, the experimental value is what you recorded or calculated based on your own experiment in the lab. And the data we just looked at from page 10 in your packet, we were looking at their data from their experiment in their lab. The true value is the textbook or the literature given value. This was, they were measuring the weight of a paperclip. Well, there's a accepted or given value of the weight of a paperclip. The hope is that if everything goes perfectly in lab, which it almost never does, your experimental value will be very close to the true value, as in groups 1 and 4 in the data from page 10. So the exact steps to calculate percent error is step 1 to calculate the error, experimental value minus true value. Step 2, divide the error by the true value. This will give you a decimal number. And step 3, convert that to a percentage by multiplying by 100 and adding the percent sign. This all is incorporated into this formula. So experimental value minus true value divided by true value times 100. Step 1, step 2, step 3. Example. This example was actually printed incorrectly, so I want to go through this with you to make sure everybody has the right information. They forecast 25 millimeters of rain, but we really got 20 millimeters of rain. So our experimental value, what we actually got in a lab, is 20 minus what we were expected to get, 25. A forecast tells you what you're expected to get. So 25. 20 minus 25 divided by my expected or true value, 25. So 20 minus 25 is a negative 5 divided by 25 times 100 is a negative 20%. So there was an error by 20%. So the estimate was too low, a negative 20%. I'll do number 1 with you. So directions for each of the following situations, find the percent error involved. Be careful in determining the true versus observed value. Observed is the same thing as experimental. I'm intentionally using several different words for observed, experimental, your results, things like that, because you will see these words in many different manners on both your tests and in the classroom for labs. So for number 1, Samantha S. Sloppiness measured the volume of her soda before she drank it for her mid-morning snack. She measured the volume of the 12-ounce bottle to be 14 ounces. So we need to look at our steps. Step 1, calculate the error. Experimental value minus true value. Samantha's experimental value, her results were 14 ounces. So I have 14 minus my true value. So it's actually a 12-ounce bottle, so my true value is 12 ounces. So 14 minus 12. So then we go to step 2. Divide the error by the true value. You will get a decimal number. So divide my error, 14 minus 12, divided by my true value, which is still 12 ounces. Then we go to step 3. Convert to a percentage by multiplying by 100 and adding a percent sign. So let's multiply by 100. And my answer will have a percent sign. So when I put this into my calculator, 14 minus 12 divided by 12 times 100, I get 16.6%. Notice this is a positive number, which means I am above the actual or the true value by 16.6%. My error is more than my actual value by 16.6%. Now the answers for number 2 and 3 are also at the bottom. And we got the correct answer for number 1 right here. So you can check yourself for number 2 and 3 and complete number 4, 5, and 6 when you come to class tomorrow. I hope you enjoyed this video, and if you have any more questions, please be sure to ask.